These concrete structures look impressive, but why do they develop cracks just a few days after construction? Take a close look at the deformation of this concrete block. Are the lengths of the top and bottom edges equal? No, the bottom edge has stretched, while the top edge has shortened. Just compare the lengths before and after deformation. This means the bottom of the concrete block is under tension, while the top is under compression. Here's the problem. Concrete is inherently weak in tension.
This concrete cylinder is easily able to carry the weight. But when I hang on the same concrete cylinder transmitting a tensile load on it,
This experiment proves that the concrete is good in compression, but quite weak in tension. This weakness means the bottom portion of the concrete block, which is under tension, can easily develop cracks. So what's the solution? Introduce steel reinforcement bars to the regions that experience tensile stress. Steel is excellent at handling tensile forces. The structure we've just created is called reinforced concrete.
generally engineers use a universal testing machine to test strength of a concrete. But I'm going to teach a crude method to compare strengths of different concrete without using a UTM, a method using your car. This is my simple arrangement. Just raise the jack, you will be able to transfer a good amount of car's weight to the concrete block. This concrete block has no reinforcement and breaks suddenly without carrying much of the car's weight. In the second block, I have added a few reinforcement bars towards the bottom. Now you can see the concrete is developing small cracks at the bottom. The car is almost fully up. The block has transformed into a beautiful curve with a lot of cracks. Yet the block is able to carry the car's weight. Finally, it failed. With the reinforcement, the concrete was able to carry much more weight before it completely failed.
Another key observation, with reinforced concrete, cracks form gradually, whereas plain concrete fails suddenly and without warning. In fact, the normal concrete is brittle in nature. In short, reinforced concrete can bear significantly higher loads, and when it does fail, it provides clear warning signs. Now, let's look at a cantilever beam. It's even more interesting. In this case, tensile stress develops in the top fibers. Knowing this, you can determine where to place the reinforcement bars for maximum strength. Reinforcement bars greatly increase the load-bearing capacity of concrete. But there's an even more ingenious way to improve it further. We know concrete loves compression and hates tension. What if we pre-compress the concrete before applying any load? By doing so, we can significantly reduce the tensile stress when an external load is applied. This technique is called pre-compression. For comparison, this is how stress is developed in normal reinforced concrete. Look at the reduction in tensile stress due to the pre-compression of the concrete. But no, we don't compress concrete manually like this. Here's the practical approach. First, stretch the reinforcement bars before pouring the concrete. Then, pour the concrete and let it harden. Once hardened, remove the supports holding the bars in tension. The bars will try to return to their original length, but because they're bonded to the concrete, they can't. This creates compressive stress in the concrete. We have just made the pre-compressed concrete. This new block will have greater strength against tensile forces. There is another method to achieve the same result: post-stressing. Here, we're compressing the concrete after the concrete is solidified. Here, steel tendons are inserted via the channels in the hardened concrete. The workers now stretch the cables using a hydraulic jack, or they're keeping the cables in extreme tension. These wedges have a special role. They make sure that even after the hydraulic jack is removed, the cables won't go back to their initial state. The cables will remain in tension. This means the concrete structure should be in compression. Concrete post-stressing is preferred in heavy structural elements with a long span. Because gravitational forces act downward, it's easy to assume that forces within a structure are always compressive. However, it's fascinating to see how tensile forces can develop within a structure, and to address concrete's inherent weakness in tension, we use reinforcement techniques like these.
I hope this conceptual video about the reinforced concrete was super informative to you. And before you leave, please check out our Patreon page and try to support us. Take care. Bye-bye.